Hello and welcome to this video. In this video we are going to look in more detail at some pendulums and mass spring systems. So we've used the cases of pendulums and mass spring systems a lot to try and represent this idea of simple harmonic motion, but now we're going to look at them and see why do we feel like these things are so interesting? Why do we use pendulums all the time? Why do we even care about mass spring systems at all? These kind of questions we're going to answer. So let's first start with pendulums. And the interesting thing about a pendulum that you might know is that they're usually used to keep the time, okay? The same with mass spring systems. You'll usually have, for example, on a grandfather clock, you have that big dial that constantly swings from side to side. That's an example of a pendulum. And it swings exactly in time with the clock ticking, okay? And that is a simple harmonic oscillator. So the key thing that's actually very interesting about pendulums is their time period, okay? And it's the same for mass spring systems. So what we're going to do in this video is calculate an expression or formulate an expression for the time period of a pendulum and a mass spring system. So I'm going to first outline my approach so that I don't just go off and see what happens. Now, my approach is that I know that I can define my angular, my acceleration and my centripetal motion, simple harmonic motion, by this formula. I can say that the acceleration that this object has at any point is always going to be negative omega squared x. Now, I also know that omega I could write as 2 pi over t. So if I'm going to try and formulate an expression for t, I first need to get an expression for a in terms of x, and then I'm going to rearrange that, okay? So this is my idea in order to formulate an expression. So what I'm going to do is now set up the case for a pendulum. So in the case for a pendulum, I'm going to have some equilibrium line down the center. I'm going to have a bob at this point with some mass m, and I'm just going to look at how the forces are acting on it. Since in order to get A, I know that F is equal to ma, so if I can calculate the forces and get the resultant force acting on this bob at this point, I can then get an expression for A. So the forces acting currently are mg acting down and the tension acting upwards. Now the tension in the wire we're not really going to worry about, because what we're going to say is I want to just get a force that will be in the same direction as the acceleration. Now we know the acceleration is going to instantly go down this way, so that means I just need to resolve this force here, and I want to know this force at the bottom here. So let me rewrite this mg here, because that's just going to be the mass. Now this horizontal distance here is going to be x. That's the displacement that I have at this point, and the length of the string I'm just going to call L. And if I say that this angle here I'm just going to call theta, then this angle here must also be theta, okay? Now I'll leave you to prove that for yourselves, but you can trust me, it is genuinely true. So now if I want to get an expression for this length here, this is going to be an opposite to this, so this is just going to be mg sine of theta. So now I can say the reason I'm neglecting tension is because tension is going to go this way, and that's going to be perpendicular to this force that I actually am interested in. So I'm going to neglect the tension in the wire, or the string, or whatever it is holding it. That means my only force actually acting on this, since we're neglecting friction because this is a simple harmonic oscillator, is just mg sine theta. Now I can say that mg, if I use F equals ma, I can say mg times sine theta is equal to ma. However, I need to first specify whether I'm going in a positive or negative direction. Is always in these cases we've defined this way to be the positive direction, which means actually this acceleration or this force is in the negative direction. So I have to say this is negative is equal to ma. Therefore I can basically just cancel out these m's and say that a must be equal to negative g times sine of theta. But I don't want an expression in terms of sine theta, I want an expression in terms of x. So I can say that if I take this second triangle, I can work out from this triangle that sine of theta, so actually let me do this over here. So sine of theta is the opposite, which is x, divided by the hypotenuse, which is L. Now I can rewrite this, and I know I want it in terms of x, so I'm going to say A is equal to minus G over L times x. And now I have something where A is directly proportional to minus x. And from this, I can say that this G over L must be equal to the omega squared. Okay, because I know I have to have this constant in the middle, and since I've come to this formula here, omega squared must be equal to G over L. Now I can solve this equation, and I can say that omega is actually going to be equal to the square root of G over L. That means that 2 pi over t is equal to the square root of G over L. And I can just rearrange this, bring t up to the top, bring this down below, and I get that the time period of a pendulum is actually equal to 2 pi times the square root of L over G. Okay, now this derivation is not necessary for you to know. In reality, all you really need to understand is this formula here, but I think it is always useful to be able to understand where these come from, so this is why I'm showing you this proof of this. Now, the other interesting things that you can say from this is that this time period only depends on the length of this string and the gravitational acceleration, which means it doesn't matter. So let me write some implications of this equation. So I'm just going to rewrite the equation down here. So it's t is equal to 2 pi root L over G. This means that it doesn't matter what mass we put on this string, right? We could put a 15-ton like massive block of metal on this string, or we could put a ping pong ball. It really doesn't matter. As long as the length of the string is the same, we're going to get the same time period. Now, obviously, in real life, that's not going to be the case because we're going to end up with more air resistance in one case than the other. But if we put it in a vacuum and we just left it to swing, it would be exactly the same. So independent of mass is a big one. So it doesn't matter independent of mass. Doesn't matter what mass we put on this. It will always be the same. Okay, the time period is always the same as long as the length of the string is the same. The second thing is it's independent of the starting position. It doesn't matter if I have a starting position that has an angle of 90 degrees or I have a starting position that has an angle of 1 degree. The total time it takes for one oscillation to be complete will be the same as long as the length of string is the same. So it's independent of starting position. So this means it doesn't matter what mass we put it on it. And the second one means that it doesn't matter where we start it from. So I could have two pendulums. I could have one where I'm going to start it where this is my equilibrium line, and I'm going to start it, and let's say it has a length here of 50 meters. They're both on Earth. Let's say I put a massive block on here that is 1 times 10 to the 4 kilograms, a massive block, and then I do the same thing here, but I'm going to have an angle here that is just 1 degree. This length is still 50 meters, and I put a ping pong ball here that weighs, I don't know, 2 grams. These two will oscillate with the same time period, which is quite not intuitive, I guess. You wouldn't expect that at all. You'd obviously expect that this one is going to take longer to oscillate, but actually, as long as they're both on Earth and they both have the same length, they'll have the same time period. This means the only ways to change the time period is to change the length of the string, or the rope, or the wire, or whatever it is, or change the planet that you're on. Okay, so you need to change the gravitational acceleration. So change G. Now some questions will tell you that you take it down into a mine, because obviously if we go inside the Earth, the gravitational acceleration will change. Others will say you take it to the moon, some will say you take it to Jupiter, so on. So either change your height from Earth or go to a different planet. Or moon, I guess, would also be true. Okay. So this is kind of an interesting thing about pendulums, and this is why we use pendulums quite a lot, because they are pretty consistent. We know that G is most of the time going to be always the same, and we can always set L to be whatever we want it to be. Now we can do the same sort of process for a mass spring system. So a mass spring system. Now let's set up a mass spring system so that we can do the same approach. We know that A must be equal to minus omega squared x. So I'm going to try and get some sort of force expression that's going to give me an acceleration, and then it should be proportional to x. And as soon as I see that it's proportional to, well, minus x, then I can say what omega squared is, and then I can solve for t the same way we did the last one. Now, in this case, I'm going to take an example where, let's say I have some equilibrium line where x equals 0 here, and then I'm going to have something that's extended beyond here, and let's just say that this extension we're going to call minus x, because this is going to be the minus direction, the negative direction. So this extension is now negative x, which means that the force that's currently acting on this that is going to pull it back up is the force due to Hooke's law. So the force coming back up is going to be k, so the spring constant, multiplied by the extension, which we've already said is minus x, so that's minus kx, and that must be equal to the mass times the acceleration, and hence I can then just rearrange this one quite easily to get that the acceleration is minus k over m times x. Now k over m must be equal to omega squared. Therefore, I can say that omega is the square root of k over m. That means that 2 pi over t is equal to root k over m, and therefore t must be equal to 2 pi root m over k. Now again, you don't need to know this derivation. If anything, I would say this is probably a very weak derivation of this. But it gets the job done, you get to the right answer. So this is your expression for the time period of this. And again, we can examine this and we can say that this one is actually independent of a few other things. It doesn't matter where you start from again. So we can say that this is again independent of the starting position. So it doesn't matter if I have a spring that is extended 3 meters, or I have a spring that I've extended by 1 millimeter. As long as the same mass is attached to it and the same spring constant is in the spring, they'll have the same period of oscillation. So the only things it depends on is the mass that you've attached to the bottom here and the spring constant of the spring. It's also independent of gravitational acceleration. It doesn't matter what planet you're on, this will always be true. Right, so independent of G. So I could set off 2 identical systems, one here and one on Jupiter, where they've got really strong gravity, but actually this thing will continue to oscillate with the same time period on both planets, which is again kind of a weird thing to think about. It'd be the same on the moon, where you imagine everything floating around. Actually, if you started mass spring system bouncing up and down in an ideal physicsy world, it would be the exact same as if you were to do it in a lab at school. So it pans down to the only ways to change the time period are to increase or decrease the mass, so change the mass that you've attached, or to change the spring, so change k. But you could do anything else to it, take it to any planet, start it from any position, and you'll always end up with the same time period of oscillation. Now, these are two very powerful equations that you can use for most of these problems in order to solve them. One thing I will say is it's probably very rare for them to actually ask you specifically, this is a pendulum or this is a mass spring system. They'll usually give you some sort of setup that will resemble a pendulum or a mass spring system, and they'll leave it up to you to be able to identify that that is a spring system or that is a pendulum. So I would say definitely, as always, you want to do as many practice questions as possible so you can spot when they're actually trying to ask you, this is about a pendulum, this is about a mass spring system, even if it's maybe the first thing I can think of off the top of my head is maybe a child on a swing. That could be a pendulum. A crane that has a mass attached to the bottom of it that swings as the crane turns, that's a pendulum. So on, right? You can do multiple things in the real world where you're actually just talking about pendulums or mass spring systems. But hopefully these two equations make sense. The derivation of them makes sense. Even if it doesn't, you don't have to worry about it too much. But I would say try and make sense of it, because it will not only help you with this topic, but it will also help you going back to AS mechanics as well. Thank you for watching.